So, the surface force is typically represented using a second order tensor which is called, let us say, sigma ij. What do I mean by sigma ij? Sigma ij is actually a force, okay, acting in I direction on an area directed in j direction. So, you can always define a vector normal to any area that you consider, and let us say j is the direction and I is the direction of the force. Okay. So, that is how you will represent your surface forces. For example, if you talk about sigma x y, okay, that means you have a force which is acting in the x direction, but it is on an area that is perpendicular to y direction. So, that is the idea of defining it. So, if you want to mark here, let us say in our diagram we want to represent sigma. So, remember, so how many components of sigma would be there? There will be 9 components. So, you will have a sigma x x, you will have a sigma y x, you will have a sigma z x, you will have sigma x y, sigma y y, sigma z y, sigma z sigma x z, sigma y z, sigma z z. Okay, there will be 9 components of the stress and is often conveniently represented as a matrix, and that can be simplified, or that basically constitutes 2 parts. Okay, this is the total stress. That stress can be either due to pressure or due to shear stresses. Okay, so we said there are 2 kinds of surface forces, pressure and stress, shear stress. So, the pressure is typically denoted by P, the shear stress is, let us say, we will use tau to represent that. Okay. So, now the pressure, it does not matter what, or the pressure is essentially always the only component of pressure that is going to come up are either Pxx, Pyy and Pzz. Okay. Pressure is not like shear stress. Shear stress are the ones which will have other components. So, what I am trying to say is that if you look at your total surface stresses, that is going to be minus P plus tau xx, tau yx, tau zx. So, P, okay, will have a component in x direction, okay, and then in addition you can have a stress that will come from viscosity, and we typically use negative sign for P because pressure is considered as compressive. Similarly, you will have a tau xy minus Pyy plus tau yy and then tau zy, tau xz, tau yz minus P plus tau zz. Okay. So, this is if you want to write your surface stresses as pressure and shear stresses, okay, viscous stresses separated. So, I can also show it schematically. So, for example, let us look at sigma xx. Okay. Sigma xx is what? It is a force that is acting in x direction on a plane in x direction. So, if you look at sigma xx would actually be this. Now, I can also define so the area that I am looking at is this, the one which is perpendicular to x direction. Okay. So, I can define 2 more forces. I can define a force that is acting in y direction on this area x. So, a force that is acting in x direction, sorry, acting in y direction on this area x, that I can write it as sigma yx. I can talk about another stress that is acting in z direction. So, that will be sigma zx. Similarly, if I consider another point, let us say that this on this plane. So, that plane is a plane that is perpendicular to y. So, if I define a sigma yy, that will be a force that's acting in y direction on the area y. I can define a force that's acting in x direction on this plane y, so that we will write it as sigma xy, or I can write down a force that's acting in the z direction, so that will be sigma zy. Okay. So, these are the various components of forces or various components of this matrix, okay, the stress that we are talking about. Now, what we really need is that we need to write down how these stresses come as part of the force that we are talking about, because that is the expression that we are really looking for. In other words, we need to write down the stresses as forces. So, we have already done that in the context of a equilibrium system, okay, a fluid which was under equilibrium, which was not flowing, a static fluid, and there we found that the force is essentially written as gradient of pressure. So, we found that it is not pressure that is really important, it is the difference in pressure that is what is going to be important. It is the gradient of pressure that generates a force. Similarly, we will get something similar here. We need to find out how is stress going to be reflected as force. So, let us make another diagram. Okay, let us consider fluid element. Okay, our usual notation x, y, z. Let us look at one of the faces, say the red face. Okay. So, there I have sigma xx So, sigma xx is acting on that side. Okay. So, if sigma xx is acting on this side, on the other side we can say that the stress is going to be sigma xx plus del by del x of sigma xx, or if we want to talk about the force, that is going to be multiplied by dy dz, and on this side as well it is going to be multiplied by dy dz. In other words, the forces that is going to come in x direction from this particular component, so difference, okay, the difference between the force acting on the left side and the force acting on the right side is minus del by del x of sigma xx. So, here is a dx dy dz. Now, is that the only force that is acting in x direction? No, there can be forces that is acting in x direction on the y phase as well as on the z phase. So, for example, there. So, that is your y phase, and on that there can be a shear stress that is acting in x direction, which is given by sigma yx, and here there can be a shear stress that is acting in the opposite direction. So, we will say that this is sigma yx, and therefore, this is del by del y of sigma yx dy sigma yx plus del by del y of sigma yx dy. And if you want to talk about it as force, it is times dx dz. So, this is times dx dz. So, that is a force that is acting in x direction, but on the area that is that is perpendicular to y. So, equal to this, then plus minus del by del y of sigma yx dy dz, and similarly there is going to be a contribution that is coming from the z faces minus del by del z of sigma zx dx dy dz, right. So, that is the total force that is going to be acting on this fluid element. Okay, so I need to make a correction here. So, I wrote down it as minus, but if you look at this, our coordinate system, the positive is towards the right hand side. Okay. So, since that is the right hand side, the force that is going to be positive is the side. So, this is the positive side. So, really the force, if I want to talk about the net force acting in a particular direction, it is going to be this quantity minus that quantity, and therefore, each of them got to be pluses and not minuses. That is a mistake. Okay. So, the force is defined positive in the positive x direction, and therefore, the net force that is acting in the plus x direction is given by that extra contribution. So, that is the force in x direction. Similarly, you can derive a force in y direction and you can derive a force in z direction as well. But we have defined sigma xx. So, sigma xx as minus p plus tau xx, sigma yx as tau yx, sigma zx as tau zx. So, we can actually use that fact and simplify this further to write it as del by del x of minus p plus tau xx plus del by del y of tau yx plus del by del z of tau zx times dx dy dz. Okay. In other words, this is going to be the force density. Okay, this is going to be the force density that we really need in x direction in the expression that we had derived here. So, that was the expression that we had derived here. So, there is a rho g that we have we have it from the body force, and then we have a shear stress term that is going to come here. So, we can now use all this fact and simplify and write down our momentum equation as rho times. So, if we write down the x component that is dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z. So, this is what we had earlier. What we had on the right hand side, I am just writing it on the left hand side. So, remember this was the expression that we had gotten, and we had this as the total, the material derivative of velocity field. So, I have just written down the u x component. So, this is v has x, y, z. So, from this the v, from that v, I am just writing down the x component. Okay, the x component of v, the x component from there, the x component from there, and the x component from there. So, that has to be equal to the shear stress, the surface forces that we have calculated, minus dou p by dou x plus del by del x of tau xx plus del by del y of tau yx plus del by del z of tau zx plus rho gx, which is the body force. Okay, so that's a full expression for the momentum conservation in x direction. Similarly, we can write down the y part. I'll just write down rho times, now we are talking about the y component of velocity. So, that is dou v by dou t plus the substantial derivative of v, which is u dou v by dou x plus v dou v by dou y plus w dou v by dou z is equal to minus dou p by dou y plus del by del x of tau xy plus del by del y of tau yy plus del by del z of tau zy plus rho g y, and the z component is going to be dou w by dou t plus u dou w by dou x plus v dou w by dou y plus w dou w by dou z is equal to minus dou p by dou z plus del by del x of tau zx plus del by del y of tau, sorry, this is now notation is x z tau y z plus del by del z tau z z plus rho g z. Okay, so this is what the equation of linear momentum written for the fluid element, okay, in the Euler frame of reference. It just looks complicated, but actually it is not that. Okay. So, the left hand side, if you look at, that is nothing but the substantial derivative, okay, the substantial derivative of velocity, and the substantial derivative of velocity is nothing but acceleration. So, the left hand side really represents the acceleration, and if the left hand side is acceleration, the right hand side should be force. Remember, we have written it for unit mass. Okay. So, this side is going to be nothing but total forces. So, the forces consist of two parts. One is that you have got gravity forces, and the other is that you have got viscous forces, and then we have got pressure forces. So, in each equation, acceleration is equal to pressure plus viscous forces plus gravitational forces, that is all it is. Now, it is convenient. So, remember, we did not write what tau is, we just defined tau as a shear stress, we defined it as a surface force, and we said that is what is acting on the fluid element, but we need to further simplify it in order to use it further, okay, because if you write it in this particular form, there are too many unknowns. And what are the unknowns? For example, velocities are unknown, the way it is written, pressure we do not know, shear stress we do not know. That is where Newton's law of equation comes into picture, okay, or Newton's law of viscosity comes into the picture. We can use Newton's law of viscosity to write stress in terms of velocity gradients. Okay. So, stress, if you write it in terms of velocity gradients, the unknowns, the stress being unknowns will go away, and instead we are going to get velocities. So, we can try to do that now. So, each of these quantities tau xx, tau yx, tau zx, each of them can be written down in terms of now viscosity. So, tau xx is nothing but 2 mu times dou u by dou x, tau yx is nothing but mu times dou u by dou y plus dou v by dou x, tau zx is mu times dou u by dou z plus dou w by dou x. Remember, when we derived Newton's law of viscosity, we simply connected stress with rate of strain. Okay, here I have written down in a much more general fashion, where each of the components of the shear stress is related to what you call as the velocity, how it is connected to the velocity gradient. Okay. So we can now calculate what for example, what is del by del x of tau x x is. So del by, so let us just take the right hand side of this, so which let me represent as that. So I am just going to take that and I am going to simplify. Okay, I am going to simplify that. So what I have is del tau x x by del x plus del by del y of tau y x plus del by del z of tau z x is equal to del by del x of 2 mu dou u by dou x plus del by del y of mu into dou u by dou y plus dou v by dou x plus del by del z into mu into dou u by dou z plus dou w by dou x is equal to, this is 2 mu times del square u by del x square plus this is mu times del square u by del y square plus mu times del square v by del x del y plus mu times del square u by del z square plus mu times del square w by del x del z. And this can be further simplified. So I will write this as mu del square u by del x square. So I will mark the things that I am going to do. I am going to take half of that, I will write this and I will write that together, mu times del square u by del x square plus del square u by del y square plus del square u by del z square, and then the other quantities, which is half of that, this and this put together, mu times del square u by del x square plus del square v by del x del y plus del square w by del x del z. Now this particular quantity I can also write it as, so this quantity I can write it as mu times del by del x of del u by del x plus del v by del y plus del w by del z. But if you think about the equation of continuity for the incompressible fluid, this quantity is 0, right. So this entire expression is 0 for an incompressible fluid. That is what we had derived, incompressible fluid. So that means it is not there, or in other words it is not there. So what I wanted to tell you is that the right hand side of the equations that we derived essentially simplifies into this particular form, and therefore I can substitute that back into the equations that we derived. So the one that you are seeing in this purple color we can now replace, and if we replace it, and we can do that for other equations as well, and then the equations simplify further, and the simplified equations would be rho, okay, so that represents really mass times the x directional acceleration, which is dou u by dou t. Remember, it is a substantial derivative, u dou u by dou x plus v dou u by dou y plus w dou u by dou z should be equal to the pressure forces minus dou p by dou x plus the shear stress forces, which we have calculated it as just this quantity. Okay. Now, this quantity can also be written some further. Okay. So, this is nothing but mu times del square u, where del square is the Laplacian operator, right. Laplacian. Del square is Laplacian. It simply says it is del square by del x square plus del square by del y square plus del square by del z square. Okay. So, that is nothing but just del square u plus rho g x. Or if you like, you could also write your left hand side using your substantial derivative definition, which is rho times du by dt. Okay. So, that is one way to write it. Now, similarly for the y momentum equation, it would be simply rho times dou v by dou t plus u dou v by dou x plus v dou v by dou y plus w dou v by dou z is equal to minus dou p by dou y plus del square v plus rho g y, and the z momentum rho w by dou t plus u dou w by dou x plus v dou w by dou y plus w dou w by dou z is equal to minus dou p by dou z plus del square w plus rho g z. Okay. So, that is the equations of linear momentum expressed as only in terms of velocity. So, if you look at now, you only have u, v, w and pressure as the unknowns. Okay. So, let us see, unknowns are u, v, w and p. So, that is 4 in number. Okay. How many equations are there? You have 3 equations here, equation of x, y, z linear momentum, and then you also have conservation of mass. So, you will have 4 equations, 4 unknowns, and given any problem you will be able to solve and find out the solution. Okay. The equations look a little more detailed, okay, but there are many cases where it can be simplified and solved, and we will look at some of the cases later on, which will give us some insight into what does the fluid flow look like in a given situation. So, these equations that we have derived, we have assumed Newton's law of viscosity, we have assumed incompressibility. So, this is really applicable for incompressible fluids, and we have also used Newtonian assumption. In other words, we have used Newton's law of viscosity. And of course, we are using we have expressed this in Cartesian coordinate system. Okay.